Welcome back, everyone, to Robotics 101. This is a training for ag teachers and ag tech coaches. My name is Andy Lindsay, and this right here is the link to the slideshow, which I will copy in a repeat to the group chat. There it is. And today, now that we've got our Cyberbot robots constructed, we're going to go ahead and work on navigation. We'll start actually by testing the servo connections, just to make sure that the servos that were running during the previous session are still running. Secondly, we need to make sure that the left servo on the robot is connected to the port up here labeled P18. So that's this servo here on the left, and the right servo is connected to P19. So let's take a look at that. I'm going to go ahead and paste in, well, actually I might have better, yeah, we might, I'll hold off on pasting in a link and just talk first about wheel direction. This is a slide that for most of us is probably not something we think about reminding anybody about, but with students and their digital devices, the old analog clocks may or may not be on their radar. So, I remind them which way counterclockwise and clockwise are using an image like this one. And these slides, you're welcome to grab all the images if you, for uses in the classroom that are for the Cyberbot. And so, yeah, this is another resource. Now, as far as controlling the servo speed, last time we had a script, which I'm going to paste to you again, that had statements like this in it, where it said bot of 18, and you're probably thinking, okay, yeah, that's probably that port number 18, so that'll be going, in this case, to the left servo, and we'll look more closely at left and right servo and port 18 and 19 momentarily. But anyway, bot of 18 dot, and when I say of, that's in between parentheses. So bot 18 in parentheses, or bot of 18 dot servo underscore speed of 65. And 65 is a number that sets both the speed and direction of the servo. So,
hey, Andy,
yeah, go ahead.
I apologize.
Yeah, I was going to say the same. We don't see your screen. If I think you are intended.
Yes, I was intending to be showing you the screen. I'd better back up a little bit here. All righty. Can you see my screen now? Let's see, share and screen share. There we go.
That's a whole lot better.
Okay, good.
Yes, it works now.
All righty. Well, let me back up a little bit here. Okay, so as I was saying, welcome. This was the screen I intended to be showing. And then this came up when I pasted you the link. And then the subject of bot navigation is next. And in the slides, these are links to, this is a link to the cover page. Are the servos centered is grayed out because we won't need to do that. Our servos are factory centered. With other bots, and sometimes with this bot, depending on supply chain situations, you'll get servos with little holes in them, a hole in each servo where you put a screwdriver and tell it to turn at 0 speed, and then it'll turn maybe slowly, and you'll put the screwdriver in and turn it back and forth until the servo stays still, and then it will be centered. So that's what Are the Servos Centered is about. And at the beginning of that, it asks, well, we'll take a look. It asks if your servos are factory centered. So, and basically, if they are factory centered, you just go ahead and skip to the next activity. Otherwise, you go through here and adjust the servos. Anyway, so this is the front of the robot. Again, it's a tail dragger, so this is the tail ball or tail wheel at the back of the robot. And the front of the robot, you can imagine that maybe you're sitting on top of this white prototyping breadboard area, looking forward. And so if you're turning left, that's going to be this direction. If you're turning right, it'll be that direction. And so here is the actual chapter in learn.parallax.com. And you can also follow these other links to the various activities within the chapter. Again, we're skipping Are the Servos Centered? And this is where we were talking about the clockwise and counterclockwise, and folks maybe realize, and thanks for letting me know that I wasn't showing you this slide. So anyway, this is an image that you can grab and use as a reminder to students. I heard on the radio that a rule was passed in Great Britain to only use digital clocks in the classroom because students were having difficulties reading the analog clocks. I mean, it was a fairly reliable station that prides itself on accuracy, so it might be real. Anyway, there's a slide for a reminder to the students. And then now we're talking about servo speed. So there were 4 statements like this that were in the program that made our wheels turn last time. And these statements, this number right here, and this is a nice thing to keep on hand and even print out for the students, because that way they have a little legend of, oh, okay, it's P18. That goes to the left servo. So baud of 18 means I'm controlling the left servo, and then servo speed. And then they have a nice little speed chart here where basically if you're, and there's some plus and minus in this that's not shown here. It would have cluttered the diagram too much. But between -15 and 15, the servo should stay still. Outside that range, if you gradually increase the number that's here in the script, what you will see each time you run it with an increased value is that it will turn counterclockwise faster and faster until we get up to about 115. And again, there's still some, there's some margin for error in there, but around 15 is when it should start turning. Around 115 is when it hits its max speed. It'll certainly accept up to say 200, but that's asking more than the servo can give. So we just call that the overdrive range. Now, if we do -15 to -115, that will cause a gradual increase as we increase the speed in the negative direction. So -15, -20, -25, that will get faster and faster in the clockwise direction. Now you can also use none. And what that does is it turns off the control signal to the servo entirely. So it just stops doing things. The control signal that goes to the servo has to repeat 20 times, or pardon me, 50 times, 50 times per second. Yeah, 20 milliseconds. So every 20 thousandths of a second, the servo needs to be reminded what it's doing by the processor. But we don't have to program at that low level. We can just say this statement, and then as long as there's not another statement to overwrite that servo pin and speed, and again, 19 is for the right servo, 18 is for the left servo. And we'll find out soon enough if our robot goes backwards, whether or not we've got the left servo connected to 18 and the right servo connected to 19, or if we need to unplug and swap them. Okay, so, and this is another legend I use with the students so that they know which is the front, left, right, and back. And here's a zoomed in one of it. And then an interesting thing to talk about is the idea of, depending on which side of the bot you're looking at, the wheels might be turning in opposite directions just to make it go forward. So some students might think, oh, well, you make both wheels turn the same direction and it'll turn forward. No, in fact, it'll rotate in place as opposed to moving forward. So to move forward, looking at the clockwise side, looking at the right side of the robot, this wheel has to turn clockwise. Now, to do that, we will need a negative value. Then on this side, on the robot's left side, so this is the right, and this is which is closer to the 3-position switch to turn power on and off. On the left side of the robot, the left wheel has to turn counterclockwise for forward motion. I mentioned that the servo has to be reminded 50 times a second of what it's supposed to be doing. And for that, what happens is if we say baud of 18, negative 200, so that's overdrive, top speed, clockwise. What's happening is that it's delivering. Well, actually, I'm gonna explain this a little bit differently. To make the servo stay still, down here at the bottom, if 1.5 millisecond brief high signals that turn on a light, if a light circuit were connected to the pin, and then low signals for the remainder of 20 milliseconds, if those brief high signals last for 1.5 thousandths of a second, that's what makes the servo stay still. Now, we can add, using 200, what that does is it adds 0.2 milliseconds to that signal. So instead of 1.5 milliseconds, it is 1.7 milliseconds. And that's full speed overdrive counterclockwise. If we use negative 200, what that's doing is subtracting 0.2 milliseconds, and we end up with 1.3 milliseconds, which is overdrive clockwise. And then everything in between, like if this number was 50, then these pulses would be narrower, and it would be 1.55 millisecond pulses. So this is actually the number of millionths of seconds that is added or subtracted to 1.5 thousandths of a second. And so another way to think about it is like this is adding 0.2 thousandths of a second for that 1.7 millisecond pulse separated, or that repeats every 20 thousandths or 20 milliseconds. And what that ends up meaning is that 50 times a second. If you divide 20 thousandths into 1, you find out how often this repeats. It's 50 times a second. And this is just kind of for anybody who wants to know. And well, I should say that this is a little talk about signaling and timing diagrams, which are pretty common in electronics, but it's not necessarily required to understand this in order to use the robot or program it. But if some students ask why, this slide does have the answer to that. And then there is discussion in learn.parallax.com. I should mention that these images are all coming from the learn.parallax.com site. This is just a little graph of, okay, here we are at 0, which is 1.5 millisecond pulses, and around 0, and notice that it's not perfectly in the middle there. It's a little, this particular servo that was tested is a little to the left. It seems to be starting to move the wheel at a larger negative value than the positive value. So it's a little shifted. And I did mention there are plus or minuses with servos. And okay. All right, here we go. So this is another nice legend for the students with bot of 18 being the left wheel. And if we wanted to go at roughly half speed, we'll use 65. And anything between none or 0 and 115 will give this side forward motion. Likewise, anything between none and negative 115 will give this side forward motion. This is the script from learn.parallax.com that we ran last time. And so now, hopefully, it'll make a little bit more sense. It used to say when we did the step counter exercise, we said from microbit import star. Whenever we want the microbit to talk with the cyberbot, we want to say instead from cyberbot import star. Now, if you want a script to work without being plugged into the cyberbot, you'll want to say from microbit, because the first thing that this cyberbot module that's added to a project does is it waits for the cyberbot board to respond to the microbit. So if you have the microbit outside the cyberbot, not connected to it, you'll see that this doesn't start. But if you change this to microbit and then don't use anything that depends on the cyberbot, like these bot servo speed statements, then it'll work. So remember, when connected to the cyberbot and working with the cyberbot board, use from cyberbot import star. If you're just using the microbit and like the display or something, then use from microbit import star. All right, so what this does is it's going to roll forward at roughly half speed. And then the sleep 3000 right here will make the microbit do nothing for 3 seconds. Well, during that time, on its own, the cyberbot board is going to keep repeating its signals to the servos 50 times a second. So it takes care of this without us or the students having to think about it. So these two statements here start the wheels rolling, and then they keep rolling for 3 seconds, 3,001 thousandths of a second. And then after that, the script moves on. And here we're turning the wheel speeds off. How does everybody feel about that? Is that making a little more sense than maybe it did last time? Do you have any questions before we basically repeat this exercise?
I do have a question.
Okay, go ahead.
Yesterday you mentioned, or yesterday, Monday you mentioned, um, there was like a couple steps to programming, and so if I'm reading this, you're telling the motor what to do, then you're telling it for how long, and
Hmm.
then you're giving another command from that point. What were those steps that you mentioned um, yesterday? There was like four criteria or something like that to a piece of code, or
Yes, there are five basic things that code can do. Let me see if I can get back to that. Um, let's see here. Ah, yes, it was another document. Um, see, I linked that in right here. So this is slide 27. I'll go ahead and paste in this link again. Bear with me while I get my little Zoom menu visible. Okay. Okay, so that is the link to the document that has programming in it. And glad you asked about that, because what we're going to do with the Cyberbot is okay. So
I
you're right,
found
it
it.
was
I
four
found it
criteria.
right there at the top. Got it. Perfect. Thank you.
You are welcome. Yeah. So communicate, remember, decide, um, repeat, and calculate. So communicate, remember, calculate, decide, repeat. Those are the main things that scripts do. On top of that, scripts pile a bunch of nice things. Um, for example, later on, so these are all examples in the basics, but so at repetitions, that's the end of the basics. And then then this little cheat sheet takes us through an example of reading a button and displaying it. Um, and then this is where the niceties start coming in. Like, for example, it can store, instead of just a letter or a number, it might store a list of values. It can also store, this is called a dictionary, and don't worry about this right now. But if you do go through this, you will see this. And this dictionary is actually very useful when it comes to the radio control stuff. Like I mentioned tilt control on day one. Well, um, this thing will have button and X tilt and Y tilt, and then there will be corresponding numbers that come with that. And when it's packaged up in here like this, then it can be sent over the radio. The receiving robot will get it, and it'll go and look for, hey, what's the button state? And it'll find out that it's true or pressed, or maybe it'll find out that it's false and not pressed. Hey, what's the X tilt? Well, it's it's closing in on 90 degrees, so we need full speed. So that's actually, this is an example, I'm jumping ahead, of dictionaries and how they are used. And so this little tutorial after the basics, we go to abstractions. And this abstraction is, and these abstractions are data handling. So this is keeping a list of values instead of having only one value stored with one variable name. And now we can store a whole list of values. Likewise with the dictionaries, we can store a list of values that have names and corresponding values. And then a string is the most simple version of a collection. And we did already use a string on the first day. And then strings have all kinds of little features, like we can go and grab part of a string and print it, and we'll see that that we only get from the 7th through, I believe, the 10th character. And functions, and it goes on for a while. Exception handling, that's the thing that's needed to prevent a web page from freezing when you type in something that the developers didn't expect. So those are additional things in Python, and it does go a little bit beyond there. But for our purposes, and for the robot programming, for most of what we're doing, these are the basics right here. All right. Any more questions before we start using some of the navigation with the robot? Okay, so let's give this a try here. The first thing that we need to do is go back and make sure that we're starting with Cyberbot template with Blink. So again, we're gonna do the speed test, and we need to grab either, if you saved the script last time, you can simply reopen it. But what I'm going to do is send you back to this page and have you re-download Cyberbot template with Blink and open it with the Microbit Python editor. So here it is in the chat. And I'd better close some of these pages to keep my processor cool. And so you want to download that. Probably shouldn't have closed the page yet. Yes. Okay, so we're going to go to Script, Servo Speed Tests, right-click Cyberbot template with Blink, select Save Link As, and save it. It got auto-appended with a 1 because I've done that before. Then go to the Microbit Python editor, hit Open, and grab that project. And then I'm going to clean it up and paste in what we left off with last time. Except for instead of looping, as we did, I'm going to do it just pretty much as written in the lesson. Okay, so Okay, this might not be identical, but it's going to be close. I think it was that. And then we did that for 3 seconds. And then we turned both servos off with none. All right, I'm pasting. So you'll want to first open Cyberbot template with Blink and then paste this over it or type it in. But there it is in case you want to paste over it. And this is going to be for, we'll be adjusting it to be like this soon, but I'd like you to start with the one I pasted in. And what we're shooting for with this is when we run it, if we have batteries in and set it to set the 3-position switch here, the PWR switch. We want to set that to 2. And then there's a button underneath the microbit that we can press and release. It's right by the it's right between well, it's basically there's a small button right next to the USB cable, and when you press and release that, it will restart the script. And what we want to see is the robot arcing forward and to the right. If it's arcing backward and to the right, then that means that these cables need to be swapped. The one plugged into P18 needs to go into P19 and vice versa. There's a checklist in the tutorials that basically asks, do you have your batteries in? Is the power plug connected into the jack? And is the switch set to 2? If it's set to 1, you'll still have a green light on it, but everything else on the system is alive, just not the servos. But when you set it to 2 and press and release the reset button, then you'll get that little maneuver out of it. And so go ahead and give me a thumbs up when you've gotten that maneuver out of it. Got 1 thumb, 2, 3, very good. I think that's a 4, 5, 6, 7, 8. Oh, excellent. All right, now, does everybody have it going forward, or do we need, does anybody need a little bit of time to swap these 2 cables?
I actually have a question. Mine is doing that pattern, doing it okay, but it doesn't stop.
Oh, interesting. Well,
And I have it exactly how you have it on there. So,
okay. Go ahead and try copying and pasting the one from, and if you want to save, uh, if you want to save what you've got, that's great because you can reopen it. But I would try copying and pasting this directly just to see if there's some subtle missing element. Or if you copy and paste your code into the chat, I could also try it out here.
What color is the none in your code at the bottom? If it's not purple, that might be why.
yeah,
Interesting.
yeah, it's purple or
Oh, okay.
blue.
Yeah, like this would be an example of none that is not purple. You might also be running the the last time I started us with a script that was actually in a loop and it stopped everything. It looked more like this.
Oh, mine does say while true.
Okay. Yeah. So this while true. So what you'll want to do is you'll want to shade all the stuff below while true and hold the shift key and hit the tab key to outdent it. And then you'll need to get rid of the while true, which you can do either by deleting it or by just adding a hashtag symbol, #, in front of it. Either way will remove while true from the script.
Okay, now it works.
Perfect.
Perfect.
And so we all want to make sure that our robot is arcing forward. And again, if it's arcing backward, well, I'll just show you real quick what happens. Okay, so here's a cable swap. So it's turning backwards and to the left instead of forwards and to the right. I'm oriented here so that we can see it better. So here is our backwards and to the left. And if we swap the cables again, I'm emphasizing this because this happens to a lot of students. Now we should get forwards and to the right. All righty, ready to do the next thing? What I'd like you to do is take lines 3 through 5 and copy them and then paste them right below the sleep, right below the sleep 3000 and on the far left, so that you essentially have two routines that that do that curve. And then let's try to make it go forward. So we'll say 65 and -65. So that should take us forward. And then we'll turn in place. And I'll talk about this in the slides. But this is left wheel counterclockwise for forward. This is right wheel clockwise for forward. This is left wheel counterclockwise, which is forward. But this is left wheel counterclockwise, which, remember, it's the reverse direction. So this is backward. So with one wheel turning forward and the other wheel turning backward, the bot's going to rotate in place. And I'm just going to guess that for me, 1.25 seconds, or I'll just say 1.2 seconds, is going to give me the 90-degree turn I'm looking for. So what I want, the end goal is to have our robot go in a square. And so what we're going to do first is tune that forward and 90-degree turn. And so incidentally, in the upper right, you might, if you shake your mouse over the, for anybody who doesn't have two monitors, if you shake your mouse over the zoom, a little view icon should appear in the upper right of the of your zoom window, and you can change the view to exit full screen so that you can put your zoom side by side with your microbit editor. And I'm navigating to a spot where hopefully, let's see if we can find it here. Okay, so here's an example of a full zoom window. And then here is, if you click the view drop down, there's an exit full screen. So for anybody who's on a single screen, you can exit the full screen and you can put it side by side with the editor. And that's going to be much like what I have here with the document camera over the robot and the editor on the other side. Okay, so for me to keep this inside the bounds of the document camera, let's try 2000. Hmm, 1200 was close. Now, if it turns too far, you'll want to have it turn in place for less time. If it doesn't turn far enough, you'll want to increase this time. So this is the turning in place. So this is forward. This is turn left. So I'm going to try 1100 here. And if anybody shouts out and says, hey, please paste your code, I'm having trouble getting mine to go, I will paste my code. Hmm. Mine is still turning a little too far at 1100 for the turn. 1.1 seconds was too much. So now I'm going to try 1 point. Wow, maybe 1 second is the magic number. Yeah, that looks pretty good. So give me a thumbs up when you've got your robot tuned to go forward and do a reasonably close to 90-degree turn. Got 1, 2, 3, 4, 5, 6.
Okay, I know it's probably something I'm off on. I'm going forward, but it's not activating a turn.
Okay, so the thing about the forward is that it's 65 and negative 65. And then you'll probably have a sleep 3000. I reduced it to 2000 to stay under the document camera, and I'll probably reduce it more. This is going to control how long it travels forward. Then your turn here, notice that they're both positive 65. That's going to make it turn left if you turn in place left. If you make them both negative 65, I'm sorry, positive 65 makes it turn right. Negative 65 in both of these would make it turn left. And then you need another delay. And then you need to have the statements again, but with none or 0 in it to keep the robot still.
It goes to sleep at number 5, but I don't get any turns after that. That's where I'm running into my problem. I was going to copy my code and see what you thought there. I'm
You
sure
gonna
it's
paste it into the chat?
Yeah, if that's okay.
Of course, of course.
Let's see.
Now I can also paste mine into the chat if that's better. Still not seeing one from you. Or wait. Oh, there it is.
Servo
Okay.
forward. There's an enter right servo forward. It looks like. That those spaces, I think, are creating the problem.
The little note there.
Yeah.
No, they look good. I mean, I'd give them some room just for readability like this, if you can see my screen. But aside from that, that's fine. Let's see. So we have 18 forward, 19 forward because it's clockwise. Do that for 3 seconds. Then this should be the turn in place. Absolutely.
Corey caught it.
Oh, then there's a 1.0 here. Is that what Corey said? Is that decimal point? Because this 1.000 is going to give us.
Yep, I see it now. Yep.
Yeah. So for everybody else, what happened? This particular bug, and troubleshooting is one of the biggest things when teaching a robotics class and guiding the students through it. So this is why I'm going to dwell on this a little bit, is because here we are all looking at it, and it took us a little while, and that is absolutely normal. And I've pulled my hair out for north of an hour on certain scripts just to find a little thing like this decimal point. And so removing the decimal point, now instead of floating point 1, we have integer 1000, which is our 1 second. And now when we run it, it should work. And it sounded like it did. Is that right?
Yep, all good. I knew it was one little thing somewhere.
Yep, that's what it usually is. Although actually, it's usually 2 or 3 little things somewhere, and you find one, and then you get a new misbehavior, and then eventually they all the bugs get squished. All right, so what I'd like to do next, and oh boy, did I lose my? Oh, here we go. Okay. And what we're doing is hearkening back to this idea right here of saying, okay, we can go forward. This is going full speed forward and then turning it a little over half speed. So the sleep number for turning is different from what you might have. And the idea that we can take these two statements, the routine for going forward for 3 seconds and the routine for going in a turn for a certain amount of time, we can take these and indent them and put them below the statement that makes things repeat a certain number of times. And so we'll go from just a forward and turn right to a forward and turn right 4 times. Okay, so here's a trick. Everybody heads up on the Zoom screen. To indent everything, you don't have to tap the space key 4 times in front of every line. You can just shade the little routine that takes you forward, and then Listexia strikes again. Okay. So you can take the script, the part of the script that takes you forward and to the right, and shade it, and then just hit the tab key. Now the editor is going to complain, but we'll fix that in a minute. But I want to make sure that everybody has their stuff indented, or you can hit Shift Tab to go back to what you had and hit Save. That might be the best way to go. So we can name it by clicking the name up here and hit forward, then right, and then save it, and then rename it forward, then right X4 maybe for 4 times. And then we're ready to edit it. I'll give you a second to do that, and then we'll go back to indenting the part that goes forward and turns. Okay, is everybody ready to indent again? So if so, and just shout out if you need more time. Okay, good. I got a thumb up at least. So the idea is to shade the lines we want to indent. And so that's we don't want to include the nuns in there, just the forward and turn part. And once you've got them shaded, you can hit the tab key once and it'll indent everything. And then for n in range, let's see, is it 1,4? And then we actually need to tell it, oh, we need a colon. There we go. So above the indented part, we'll just have you say for n in range 1,4, and let me double check. Oh, 0,4, because it starts at 0. I should have thought that through. 0, 1, 2, 3. That's going to be 4 times. Remember that a peculiarity of this particular thing is that it counts from the first number, but it bails out when it reaches the last number before ever doing what's in the loop. So it's inclusive of the first number and stops before it reaches the last number. So, and actually this value of n, the first time through, it'll store 0. The second time through, it'll store 1. Third time through, 2. And then the fourth time through, 3. And then when it gets to 4, it says, no, I'm not going to do any of this anymore. I'm just going to skip out of that indented part and move on to whatever is next. And so the important lesson to remember here is that for something like a decision or a repeat, which is what line 3 is doing, is repeating, the lines that are below and indented are what get repeated. And then if this were an if statement, it would be what happens if the statement is true. So indentation is very important in Python. And so now if we try this, and I'm going to reduce my distance traveled even further to stay under the document camera. Okay, so let's give this a try here. And it looks like I need a little bit more tuning to get it perfectly square, but it's pretty close. And the students will probably want more time to make it perfect. And you're welcome to stick with the 3,000 here. I'm just using 1,000 to get the forward distance short enough to fit under the document camera. So go ahead and give me a thumbs up when you've got it doing a passable square. And also feel free to jump in. Good job. And feel free to jump in with any questions. Oh, excellent work, everyone. I'm seeing more and more thumbs up. Now, this is an important programming lesson, and students, when challenged, will be tempted to just copy and paste that 4 times. That coding style can run you out of memory pretty quickly. And so that's why it's important to emphasize, hey, there's something built in that does one of the most fundamental things a script can do, which is repeat. And it repeats a fixed number of times. And then the little thing that you, the little maneuver that you set up will be repeated 4 times. How are we doing?
So I read ahead of you last night, and one of the cool things was I've unplugged it so I could push that reset button so it can do it without the cable attached. So I can see it do without the cable dragging along the way on my table.
Absolutely. I was lifting the cable just because I don't want to end up fussing with it. Like if I have a technical difficulty on the reconnect. and yes, absolutely. For the most part, I'm going to just do it anyway and live dangerously here. It just turns out that with Zoom, sometimes funny thing, if you're presenting on Zoom, Murphy's going to step in and say, hey, let's cause some difficulties on the reconnect. But yes, absolutely. And when you are unplugged from the USB, what happens also is that you can turn the on-off switch all the way off. And when you turn it back on, it will restart the script. And so when your USB is connected, it only, and you have a script that basically ends like this one does, that's when you have to use the reset button. When you're disconnected from USB and you have a script that definitively ends like this one does, then without USB, this thing loses power entirely. So when it wakes back up, when it gets power back, it starts with essentially the script that was loaded into it. Whereas if I plug in USB, if I turn off power now and turn it back on, nothing happens because the processor here did not lose power. Another thing is, though, if you have like something like this where
Hello.
Hey, you see my text?
Yes, I did.
Okay, just making sure.
Okay, so here we are with it repeating indefinitely. With this, it'll actually, you can turn power on and off and it'll restart from the beginning. It's only when a script definitely runs out of statements that you need to go underneath and hit that reset button. For everything else, you can turn power off and back on. And especially when you're disconnected from the computer, because there is not an alternate source of power. Okay, so let's go ahead and save our work. Forward turn right X4. Remember, you can click the name up here, update it, confirm, and then save, and you'll find it in your downloads. I don't know if it's visible, but here is the forward then right, and then forward then right X4. And remember, you can drag and drop those onto your microbit Python editor to go back and forth between your iterations, or you can hit open and it'll take you to downloads to do the same thing. And with that, we're roughly in the middle of the session, so let's go ahead and take a 5-minute break. It is now 10 minutes till 5, so let's reconvene at 5 minutes till 5. And I'll stick around in case anybody wants to ask questions, but we'll stop the recording for the break and then we'll restart it after the break. And I'll be lecturing some more, and then we'll do some other things with navigation and then build the whisker sensor circuit, hopefully. Okay, welcome back from the break, everyone. We had a really interesting discussion that I would like to try to summarize because some of the teachers had a problem where their script didn't look like, well, their script looked very similar to this, yes, but what they had instead, and I'm going to open a separate instance of the Python editor to demonstrate it. So here we are back at just a new window of python.microbit.org, and we've got the default script that displays the heart and the hello. And just as a side note, that will in fact run on the microbit. So I have the studio lights on right now. It might not seem that way because this is a little bit dark, but we're not seeing the heart and the hello perfectly because of the flicker on the microbit syncing up with the flicker of the camera and the flicker of the lights on the camera. So, but at any rate, it is displaying. And if I paste the robot code in here, the editor gets really unhappy, and it tells us about all the different errors it perceives in the script. Now, the reason it's telling us about that, and if I try to run it, things don't usually go well, and it says import error, no module named Cyberbot. If we open the serial monitor, we'll see something like that. If I try to run it again, we might see the whole message. There we go. So this is the kind of thing that we'll see when we just open the microbit editor and paste in some robot code. Now, if we instead, I'm going to copy the robot code here. If we instead start with the Cyberbot template with Blink, or any other script that already worked because we started with Cyberbot template with Blink and then modified it. So in this case, I'm pasting over the robot code. Notice that we don't have any complaints. And when I hit send a microbit, if I have the power set to 2, it does its thing, which is great. And I'm going to set the switch to 1 just to have it stop, because we saw that it was going to do its square. All right, so why did this happen? Why is Cyberbot template with Blink so magical that, that it prevents all these syntax errors? The reason is because what we have added here in Cyberbot template with Blink is cyberbot.py. Cyberbot.py is called a module, and you can see it if you click the project tab, and then you can make the project tab go back away by clicking that little hide arrow. So the project tab is in the lower left, and what we'll see is our main script. That's right here. But underneath the main script, when it says bot of 18 servo underscore speed, what it does is it says, oh, well, I don't know about that statement, but I see that there's a Cyberbot module imported. I need to go find the Cyberbot module code and see if I can find servo, bot servo speed in there. Well, here is cyberbot.py, and Control F, SCR. Oh, that's weird. Where is servo speed? Here it is. For some reason, Control F doesn't take us to it, but it is definitely in there. So that's probably a bug in the Chrome browser. But what servo speed does is it jumps to line 70 in this cyberbot.py module that's been added to the project settings. And it does the job here. And this is low-level code that not really intended to be edited. So if you click this, it's going to ask you for verification to, view third-party modules, I think is the wording that they use. And so anyway, it jumps over here, it does this job, then it comes back and sees that there's another servo speed with some different values. So it jumps back here, finds servo speed again, and then sets those values and does the job yet again, and comes back to main and sees sleep. Well, that's built into microbit, not Cyberbot, but microbit. But in Cyberbot, the first thing it does is bring in all the microbit stuff too. So, so this is why it works here. But if in the version where we just opened the default script and pasted our robot script in, well, if we look at its project settings, Cyberbot is notably missing. And that's what it's trying to tell us here on line 1. Okay, how are we doing with that? Does that start to make sense? And we can see now why we need to open either the template or a robot program that previously worked is because it's got that Cyberbot module baked into it, so that we can do this, and the microbit will know how to deal with that because it has the instructions for it. And I'm going to side note just a little further and take us to learn.parallax.com and point out that if we go to the Cyberbot Python tutorial, so I hit Cyberbot, and now we're going into the Python series. And then after getting started with your microbit, learning how to load scripts and save and open them, and then after learning how to write microbit scripts on just the microbit, the third chapter is add modules to your microbit. And what does add modules to your microbit say? Well, it says that you can download Cyberbot template with blink.hex if you don't want to think about it any further, and then go back to what you were doing. Or for a deeper dive, there's a video on how to get that module, add it to your system. And so it takes you through every step of downloading the Cyberbot, all the modules available for the Cyberbot, for all the optional add-ons, unzipping it, and then going spelunking in the unzipped folder and finding the cyberbot.py module by clicking the project tab and then clicking open and navigating to cyberbot.py and then adding it to your project. So all of those instructions are here, but it's a lot of work. So eventually, when students want to mix and match modules for other things, they will want to know this. But I figured at the start we could kind of take some of the load off by just having something ready to go. All right. So with that, just a quick question check, and then we'll move on to a little bit more about navigation. So we just finished our first navigation lab. We'll do a little bit more lecture and then go back to lab. And as always, if a question occurs to you along the way, just go ahead and blurt it out. Okay, so I need to get back to navigation. All right, so did anybody feel like their robot didn't really go exactly straight forward? Okay, I got one nod. Okay, so we all saw a little bit of curve then. I didn't, but that was mainly because my robot didn't go that far. So the way that works, or the way to adjust that, is to simply trim the speed. And so there's an activity in the learn.parallax.com tutorials. Let's see what happens. So if I click it, so here we are at forward, backward, and straightening curves. And I clicked the slide to follow the link, just because I want to emphasize that we have all this material in the tutorials, that it's not necessarily just the slide and that's all you get. No, you get, a complete written explanation. And you can also essentially harvest these images and put them in your own slides, as opposed to grabbing them from the slide. Either way is fine. And so here we have the instructions, and the instructions say, and hopefully the students will follow, to right-click Cyberbot template with Blink, select Save Link As, then open the editor, then open cyberbot.blink, then type in this over it. And so then they'll test it. They'll find out that it doesn't really go perfectly straightforward. So the next thing that we have the students do is learn about straightening out the path. And so to straighten out the path, well, we did we did what was in theory supposed to go straight, but in this example, let's say it went to the right. Okay, great. If it goes to the right, that means that this wheel is going faster and this wheel is going slower. That's what's making it curve to the right. So what do? We want to slow down the faster wheel normally, because if you speed up the slower wheel, well, what do you do if you're trying to go full speed and you want to straighten it out? So we'll slow down the faster wheel. That's going to be the left wheel. So first cut, let's just cut 10 from it. So we'll say 55 on the left wheel and then negative 65 for the same speed as before on the right wheel. And maybe that will curve to the left. Okay, well, let's split the difference. And maybe 60 for that left wheel, just slowing it down by 5, is what straightens it out. And students will have to experiment with this at whatever their desired speed is and figure out the numbers that they need to make their robot go perfectly straight. Then later on, when they're using sensors, it may matter quite a bit less. But for right now, if they really want it to go straight perfectly, they can use this kind of technique and some iterative and splitting the difference type of testing to arrive at the numbers they need to make the robot go straight. So this is a little bit about turning in place. That's the third activity. So if I follow that link, this is left and right turns, and we talk about using both negative values or both positive values. And we've got some little animations on the page to show the turn in place. And those are when the numbers are the same. Now, we can also make one of the wheels just stay still, and instead of turning in place like a Roomba might, we'll get a pivot turn. We can also do curves of varying diameters. Like with this one, the right wheel's turning, the left wheel's turning at whatever the normal straight ahead speed we started with is, and then the right wheel is turning pretty slow. Here, for a wider curve, the right wheel is turning a little bit faster. And for that, we might want to use what we did in the Learn site was left that as a challenge for the students. And then there was the Parallax Educators, the learn.parallax.com educator account that you can start. And there are solutions to these for you to view so that you can reference them if assisting students and not sure about the solution. But in general, it's, again, just experimenting with these numbers. And like, for example, we're getting a natural curve, but normally, this would be the kind of code where this wheel's going slower. And if the servos were perfectly matched, this wheel going slower and this wheel going faster would result in a curve. You make this number smaller and smaller, and the curve will get tighter and tighter. And so here is an example of a wide arc with we've slowed down the right wheel. It's closer to 0, but we haven't slowed it down all the way. Slowing it down further, we end up with a tighter arc. Everybody okay with that? All right. Then we talked about the square. And now I'd also like to talk about, well, this is a case of abstraction. Students can write a function, and this was very popular in my last robotics class, because essentially bending your mind around the idea of a negative value, or essentially your right wheel has to always be the opposite value of the left wheel, or of what you think it is for forward and backwards. So here is a way of saying maneuver. We can say maneuver, left speed with positive being forward, right speed with positive being forward, and then maneuver time, all in one line. And the way it works is with something called a function. Functions are pieces of code that you can tell the script to find, do the job, and then come back when they're done. And so here's the function code. And later on, we will actually have this function code baked into another module that's added to the project. So we won't even have this cluttering up our code. But for now, we'll just take a look at it, and I'll show you how to download the code and open it and try it out. But here is the maneuver code, and it has 3 variables: velocity left, velocity right, and time. And so when we say 115, 115, that's going to be full speed forward for 3 seconds. And when the Python runtime sees maneuver, it grabs all these values, finds the maneuver function, plops those values into their corresponding temporary variables that the function is going to use. And then it goes through, and this probably looks familiar right here. These are the statements that we've been using up until now, along with sleep. But look, now it's sleep t. So whatever number gets plopped into t gets used here. And there's also this little weird condition where if you try to use none for a speed, well, it turns out that the Python runtime chokes over negative none. It doesn't think negative none should be a thing. So, so there's this little piece of code here that says, well, if the right speed is not none, then you can go ahead and change it from negative to positive. So that's what allows us to say positive for forward for left, positive for forward for right, and then the runtime. And this makes a lot of stuff way easier. So now I need to find the download link for that. Here it is, navbasic.hex. Okay, so let me copy this link for you and paste it into. Okay, now this is going to be a little bit different from what we did last time because it's stored on Google Drive as opposed to on the Parallax site. So instead of right-click and save as, when you follow this link, it's going to take you to a black screen that says, well, there's no preview, but you can download it if you're brave. Be brave. Just hit download, and it'll put the hex file in your downloads just as everything else has been done. And after that, did I paste it in already? Yeah, it looks like I did. So after you've followed the link that came through on the chat and downloaded it, you can jump back over, make sure you've got your work saved, save, and then you can hit open and get that Nav Basics that you just downloaded and try it out. Oh, I have my 3-position switch set to 1. Uh-oh. Nav tools should be in there. Project. Okay, those are just warnings. Let's see here. This should really run. Yeah, it runs. And you can even change it to whatever numbers you came up with for runtime earlier. And okay, so go ahead and give me a thumb up when that works for you. Good deal. For those of you who are on a second computer, I'm trying to think of a way to get you the link. Oh, I see a question of why the yellow triangle. Basically, there's a bug in the Python editor here where it is saying that it's expecting me to create an object before. So it's expecting that downstairs in Cyberbot Nav Tools, which is another module that was added to add kind of another level of simplicity to the robot. What it's thinking here is that it's expecting me to create something called an object, which is one more level of abstraction beyond a simple function. Objects can contain data and functions and do all kinds of clever things for you. And you were using objects on day one when displaying the heart and displaying hello. Those are the display.show, all this stuff. So all this stuff right here, this is the display object and the show method and the image object and the heart piece of data, I believe. And then this is a sleep function that's baked into microbit. And then there's the display object, the scroll function, and we're passing it some string data. So that's how it works with objects. And objects are, again, in this case, tucked away in the microbit module. And so all I'm using here are functions. So, so here's a function for maneuver. And then I've also got some QTI functions that we're going to be using later as we're following tracks and infrared detect. There's all kinds of extra goodies here that that we'll be using later. But right now we're just trying to use this maneuver function. And the simulator, the thing that allows us to simulate things that the microbit does when we're just using the microbit. It can't simulate the cyberbot, but it can simulate the microbit. The simulator looks through all this, and it, for whatever reason, thinks that it's in a module, so it has to be an object. Well, that's not true. And so it runs all of this. Even this is saying that the script should choke, but it doesn't. And it's because of kind of a mistaken assumption on the part of the syntax checker that is inside the microbit editor. So we're using it at a little bit deeper level here than than there's support for. And so, including functions in a module, that's perfectly fine. And it does run. We saw it. And we will see that even though it's saying here that these are errors, that it shouldn't be able to run, it will run, because the Python runtime inside the microbit is fine with this, and it doesn't break any Python rules. But the syntax checker inside this web page has a little bit of a mistaken assumption about how things are supposed to work. And so that's why it's giving us all these red lights and warning triangles, but they can be ignored. That was probably a deeper answer than you were hoping for. Sorry about that. At any rate, going back to main here, I don't know why the triangles disappeared. I'm sure if I run it again, they'll come back. Yep. But again, we see it running, so it's fine. Okay, so all right, how are we doing? Aside from maybe that little bit too deep of a dive for where we're at in programming. Got one thumb up. Okay, good job, everyone. All right, so next up, what I'm going to do is mostly skip in the sequence of the web book. We're about here. We normally, after navigation, we'd make some sounds and we'd build some extra circuits, and then we'd move on to building the contact sensor circuit, which is the next one that we'll be trying. What I'm going to do in the interest of time is just talk about this, and then we'll basically cut our teeth on circuits, for those of you who are new to it at any rate, with the whisker contact circuit. And it should work out just fine. But normally we'd want to have students, with more time, do the simpler circuits and then move on to the contact sensors. But we'll make sure that everything works out fine. So here's a summary of some of the key things in the that we need as just information from the circuits and sounds chapters. One is that this white breadboard that's in front of the robot allows you to connect part wires and leads together. And the way it does that is with little rows of 5 sockets. If you plug 2 or more wires into the same row of 5 sockets, they are connected together electrically. So here, even though there's a space between the 2 wires, they're still connected. They're right next to each other, but they're on the same row of 5 here, so they're connected. And you can even connect 2 rows of 5 together to get a total of 8 available sockets to connect up to 8 wires. So oftentimes what students and some of you as you're building circuits will experience is that if you're off by a row, when you're plugging in a wire that you intended to connect, well, the row of 5 below the row of 5 you were shooting for will not allow you, that's not electrically connected. There's a one metal clip with 5 little jaws that open up as you insert the wire. And then this is a separate metal clip with its own set of 5 little jaws that squeeze onto the wire. Likewise, these 2 wires are not connected because the rule is row of 5, and because there's these little clips that are 5 sockets wide underneath that are made of metal with little jaws again that clamp on to these wires. Well, it's great that we have them in the same row, but because there's a valley here between those 2 rows and there's 2 separate metal clips, these are not connected, whereas if you put a jumper here, these are now connected. Feel free to jump in if you have any questions or clarifications about that. Otherwise, I'm going to move on. That is how to connect 2 wires. And there are also electrical supplies. So this is ground. This is the negative terminal of the battery. This would be like the black wire on your car battery. 3.3 volts is a lot less than a battery voltage, but this is what the computing system needs. So the microbit runs on 3.3 volts. Certain sensors that we're going to use will need 5 volts. So we also have a 5-volt supply built in. Then there are I/O pins here. Now what these I/O pins do is, this isn't exactly right, but it's like having access to these little plated segments right here that actually are connected to the microcontroller that runs the script we write. We have 10 minutes left. I was on slide 70. Okay, so these allow us to connect a circuit that we build to ground and to a 3.3 or 5-volt supply. And then these are the ones that we can connect the circuit to the microcontroller. And the microcontroller can be programmed to turn a light on by connecting it inside itself to 3 volts, or off by connecting it to 0 volts or ground. There's also voltage measurement and voltage synthesis sockets on here. And then we do cover stuff about circuits, like, for example, if you have a light, it has a longer pin and a shorter pin and a schematic symbol, and how electrons flow through it, how it looks in a schematic. And I'm kind of breezing by this because we'll be depending primarily on the wiring diagrams, and then mainly if you're new to circuits, use the schematic, kind of try to reconcile that, hey, here's ground, there's a ground socket, here's an LED, and then if you were to use the part to schematic comparison, you would find out that you need the shorter pin connected to ground, which we can do by a wire from ground to the same row as that shorter pin. Then the longer pin, remember this is a different row of 5, so the longer pin is connected to a resistor. So here's the longer pin connected to the resistor. Then the resistor is going to the Cyberbot board's P12 socket, which makes its way to a microcontroller that we can then program to talk to P12 by saying, hey, bot 12, write digital of 1. That'll give this 3 volts, and current will flow through down to ground, and the light will be on for half a second. Then bot 12, write digital of 0, and that will ground P12. So we'll have ground on this end of the circuit, ground on that end of the circuit, and there's no electrical pressure across the circuit, so there will be no current flowing through, and the light will turn off. We also have a little how-to on how to figure out what a resistor value is based on the color of its stripes. And so in this example, we see that there's a pair of red stripes, which are the number 2, and then there's a brown stripe, which is the number 1, and then the gold stripe is Whoopsie. And then the gold stripe is how precise the value of the resistor is, as in this is guaranteed to be only 5% off over temperature and manufacturing variations. So 221 is 22 plus 10, or some teachers like to say times 10 to the 1, but it comes out the same. And so 221, red, red, brown, turns out to be 2, 2, and 10 added, or 220 ohms, and that's a measurement of how strongly this resistor resists the flow of current. And that's all you need to know, I think, to the best of my ability, for you to get started on the whisker circuit. And so what we're going to have you do is, as homework, we'll just have you build the whisker circuit, and then we're going to troubleshoot it on the next session. Now, the next session will not be till next Wednesday, because MLK, Martin Luther King Day, is going to be Monday the 19th, if I'm remembering correctly. So I think that we'll be reconvening on Wednesday the 21st. Is that right?
That's correct.
Okay, very good then. So thank you. So what we're going to have you do is build the whisker circuit. Some of you are likely to barrel ahead and try out all of these. Just know that we'll be doing them during the session. What I would recommend doing, if you want to do extra stuff, is stay in the electronics lessons. And so I will add some, I mean, you can go nuts, really. If you can do as much of this as you want. There's instructions here for everything. And the key thing to remember is just to run and get that, that Cyberbot template with Blink. Whenever you're trying out code examples here, you'll need that, because we saw what happened without it. So there's lots of places to play here. And we're going to try the contact sensors, because that's an important thing. And one of many ways that a robot finds out if it's connected with something. So a contact sensor is good, for example, in a gripping mechanism, where the gripping mechanism needs to know that it's got hold of the object that it's grabbing, which might be a fruit or vegetable or weed. And then we're also going to, the following Monday, we'll work on light sensing, and then move on to road following. Instead of a line, we're going to have a wider road. And then after that, we will move on to another book which has the vision sensing stuff in it. And those are lessons that we've kind of cherry picked out of the larger book for the training, because they're most relevant to ag robotics, and they're the items that provide the best scaffolding to working on that larger robot. Okay, so with 5 minutes left, again, jump in if you have a question, or text me, and hopefully Ari will see it. And yeah, that's the presentation, I believe. What is this? That's Robotics 101, yes. And so what I will do is I'll talk about how building the whiskers will work. View slideshow, previous page. Whoa. Okay, so here we are at the whiskers, and I'll send you these links. So the build the whisker circuit is the official homework. So what you'll be doing is, did you notice that the build instructions had you add standoffs on the front of the robot, but just screws on the back. Well, these standoffs are in preparation for attaching the whisker circuit. And one thing about the standoffs is that you want a standoff, then a nylon washer, then that longer screw. And what you'll do is you'll loosen these two longer screws enough so that you can hook one whisker in below the nylon washer and then the other whisker in above the nylon washer. That way, when you push them against the robot, when the robot bumps into something, each whisker is on a different plane. And so they don't basically get stuck to each other. And, what we want is if one whisker is pressed, we don't want it to take the other one with it. So that's why we have the little nylon washer. So one whisker is hooked. Yes, go ahead.
No, Andy, I'm sorry.
Oh, okay. All good. Anyway, so that's what you're going to do with the whiskers. And on the robot here, those whiskers will essentially be, these are the two screws that you'll loosen. And then you will go above the nylon washer on this side, and then below the nylon washer on this side, and then retighten everything. And it'll take some adjustment to retighten it so that the whiskers kind of pass in front of the breadboard and then reach forward. And I'll show you that on the, so from a top view, it's going to look like this, where the whisker, it's hooked around the screw, above and below the washers. And then it's going to, the whisker extends in, but it should not be touching these little 3-pin posts that you plug in. And then it's going to reach out to here and reach out to here. And on the same row, you'll have a 3-pin post that you'll find in your parts kit. And then you'll have a brown, black, red. That's a larger value, 10,000 ohm resistor that will go to from 3 volts to the row. And then you'll have a small value, 220 ohm resistor that will go from that row to P9 and from that row to P7. And what's going to happen is that these whiskers should not be touching. You want to have space between the 3-pin post and the whisker as it reaches out to here. That way, if you press the whisker, it closes that gap and you have one circuit. And then when you let go of the whisker, it bounces back and the gap will be open so that you'll have a different circuit. And then our script will monitor those circuits, those two different circuits, and it will get information, either a 0 or a 1. And then we can say, if it's 0, do this. If it's 1, do this other thing. And so there is information on how the whiskers work. And if you want to try to test your whiskers, we will show no whiskers pressed. No whiskers touching. Lights off. One whisker pressed. The other whisker pressed. Both whiskers pressed. And if you're interested in working on that and just want to email me if something's not working right, I'll go ahead and try to provide some tech support. But the main plan is just to do this when we reconvene Wednesday, a week from today. And it is now 5:46 p.m. So I think that we can go ahead and, before we stop recording, top priority, very, very, very important for the sake of your batteries is, we'll turn the robot off, sure, so that it doesn't move. But what's going to happen is the microbit will still draw a little bit of juice. So we want to make sure to unplug the power jack when our robot is not in use and just leave it off to the side. And one other thing, I'm reaching for my kit and fishing out the bag that contains these small electronic parts, electrical and electronic parts that you will need to break into to build your whiskers circuit. And this is where a sorting tray of some sort will come in handy, because you can keep your loose parts in the tray. And if you have several sorting trays, either small bowls, plates, or like a little tackle box or sewing sorting plastic box, you can keep the various parts that come from the bag. You can even put wires in one compartment and certain value resistors in other compartments, and so on and so forth. And that's why it is extra nice if you happen to have something like this to do your sorting with. All right, so that's it for today, and we can go ahead and stop the recording and continue with whatever questions and answers you might have before we sign off.